Hello friends, in this video I'd like to solve the following problem from Lowell Putnam Mathematical Competition 1997, problem A3. We wish to evaluate the following integral from 0 to plus infinity of x minus x to the third power over 2 plus x to the fifth power over 2 times 4 minus x to the seventh power over 2 times 4 times 6 plus and so on, alternating, times another series inside of our integral, 1 plus x squared over 2 squared plus x to the fourth power over 2 squared 4 squared plus x to the sixth power 2 squared 4 squared 6 squared in the denominator, and so on, dx. It's a fun little problem, maybe not little, not that difficult. Here are my hints if you wish to try it yourself. Sorry, move it to the right place. Oh yes. So here are my hints. First of all, recall the Taylor series expansion for exponential function e to the power of t can be expanded as 1 plus t squared over 2 and so on. We have factorials in the denominators. Next hint, the first series has a nice closed form, and the second can stay as it is for now. Then you should try to use Tonelli's theorem to change the order of summation and integration. And finally, recall the well-known fact that integral from 0 to infinity of t to the power of n times e to the power minus t dt always equals n factorial for every natural number n. So give this problem a try, and I will see you in just a minute. Okay, so here is my solution. First, I wish to concentrate on the first series, this part right here. X minus x cubed over 2, x to the fifth power 2 times 4, minus x to the seventh power 2, 4, 6, and so on, alternating. How can we simplify it? Well, first of all, we can put x outside of our parentheses. So we have 1 minus x squared over 2. And now I wish to factor out every factor of 2 possible. So I have x to the fourth power in the numerator. And from that number 2, I can factor out 2. And from that number 4, I can also factor out 2. So I have 2 squared, 1 times 2. Next, we have x to the sixth power, and I can take 2 from this, 2 from that, and from that. So I have 2 to the third power times 1 times 2 times 3, and so on and so on. I hope that you see what's happening. Namely, we have factorials right here, so I can write it in the following way: 1 minus x squared over 2 plus 1 over 2 factorial, and x to the fourth power over 2 squared can be written as x squared over 2 squared. Next, we have 1 over 3 factorial, x squared over 2 cubed, and so on and so on. And if you recall my first hint, it's just the Taylor series expansion of some exponential function, but not exactly e to the power of x, but our argument, because first of all we have minuses in some places, and we have x squared over 2. So it's just x times e to the power minus x squared over 2. Because we have minuses with odd powers, and we have, instead of just t, for example, we have x squared over 2. So our first series has a nice closed form. What about the second series? Well, unfortunately, the second series has no nice closed form, but we can still write it in a simpler form. Maybe not simpler, but shorter way using sigma notation. Namely, first I can factor out powers of 2 again, once again. So I have 1 plus, let's say, x squared over 2 plus x to the 4th power, and I have, well, 2 to the 4th power, 1 squared times 2 squared. Next term, I have x to the 6th power, and I can factor out 2 from that, and from that as well, and we have squares, so we can factor out 2 to the 6th power, 1 squared, 2 squared, 3 squared, and so on. And you probably see the pattern. I hope that you see the pattern. Square was missing in the second denominator. Well, it's what exactly? It's 1 plus x over 2 squared plus 1 over 2 factorial squared, x over 2 to the 4th power, then we have 1 over 3 factorial squared, x over 2 to the 6th power, and so on. Using sigma notation, it's some series going from k equals 0 to infinity of what exactly? Of x over 2 to the power 2 times k over k factorial squared. Very nice. And now let's finally tackle our integral. So you know what? I will mark it as I. And now our integral I can be written in the following way. Integral from 0 to plus infinity. Our first sum was simplified to e to the power minus x squared over 2, if I am correct. Yes, I am. The second one can be written as a series from k equals 0 to infinity, x over 2 to the power 2k over k factorial squared dx. Very well. And now let's notice something. We see that this is necessarily non-negative because we are integrating over positive real numbers. And obviously here we have squares, so it's also non-negative. And that allows us to change the order of summation and integration by Tonelli's theorem. By Tonelli's theorem, we can change the order of summation and integration. So I can put first my series going from k equals 0 to infinity. Well, I can also put 1 over k factorial squared because it does not depend on x. And then I can put my integral from 0 to infinity, x e to the power minus x squared over 2 x over 2 to the power 2k dx. Very well. Now, what can we do about that integral? Well, I suggest making a clever substitution. Namely, I suggest putting t to be minus x, or rather x squared over 2. Just x squared over 2. Because dt, it's just x dx, and bounds of integration stay the same from 0 to infinity. And now we can write the following. Series going from k equals 0 to infinity, 1 over k factorial squared. And now we have our integral from 0 to infinity again. And now let's take a look. X dx, it's just dt. So dt will be here. E to the power minus x squared over 2, it's just e to the power minus t now. And what is x over 2? Or rather, because notice that that part, it's x squared over 4 to the power k. Well, x squared over 4, it's just t over 2. So it's t over 2 raised to the power of k. Very well. And now that looks like some type of gamma function integral. But first I will make one more thing, namely, I will put, because we have 2 to the power of k in the denominator, and I will put it in my series, because this does not depend on t either. So I have this series going from 0 to infinity of integral from 0 to infinity t to the power of k e to the power of t dt. And now, by the last hint which I gave you, or by integrating by parts k times, this integral right here, it's just k factorial. It can be simplified. It's a well-known result about Euler's gamma function that this is exactly k factorial squared. K factorial just. And now we have k factorial squared in the denominator, k factorial in the numerator. So it becomes just series going from k equals 0 to infinity, 1/2 to the power of k over just k factorial. And once again, what is it? Well, it's just the Taylor expansion of exponential function of argument 1/2. So it's e to the power 1/2. Or, if you wish, we can write it with square root instead of rational power. And this is our result. Just square root of e. And that's it. That is our result. Square root of e. So maybe, you know what, I will put answer right here. So this integral equals square root of e. Very nice problem, I'd say. Integral of product of double series which converges to square root of e. Very nice. So as you have seen, what was crucial? The crucial step was noticing the Taylor series expansion of exponential function, and also changing the order of summation and integration, which can always be done for measurable positive non-negative functions, which our functions were because they were continuous. Every continuous function is measurable. And that's it. Thank you for watching, and I will see you next time. Goodbye.